All right, here we go with our presentation on chemical kinetics. In this lecture, we're going to talk about obviously the speed of reactions, and so factors that affect the speed and how we can figure out how fast a reaction will go. So looking at rate laws and then some specific examples of how we can use those rate laws to determine how long a reaction might take, or factors that might control how long a reaction takes. So when we talk about kinetics of a chemical reaction, we're talking about the rate at which a chemical process occurs. And usually we're talking in units of concentration, so molarity per second. And so other than just learning about the speed of how a reaction is going to occur, we can also talk about something called the reaction mechanism, which is how the reaction happens, which obviously dictates how fast it goes. So things that would affect the rates of reactions, the physical state of a reactant obviously would affect, because in order for a reaction to take place, molecules have to come in contact with each other with enough energy. And so obviously something like a gas is going to be, the molecules are going to be much more fluid or in motion and more likely to come into contact with each other, versus a solid. Those molecules aren't really moving much at all. And then, of course, when you talk about a mixture, the more homogeneous a mixture is, the faster the molecules are going to react, because you're more likely to hit something that you're actually looking for, unless you're like, one molecule out of a bajillion, and finding the other molecule that you need to react with might be more difficult. Concentrations relates to what I was just talking about. If you increase the concentration of a reactant, you're more likely that they're going to collide with each other, and more likely for a reaction to proceed, versus if there's not a whole lot of one of the reactants, it's not going to be as likely to find the partner that it needs to find. And then temperature obviously would affect it as well. We've been talking about this before. As you have higher temperature, you have more kinetic energy, so those molecules are moving faster, so they're more likely to collide because they're moving around a lot more, and they're going to have more energy, so they might have enough energy to make that reaction happen. And then finally, the last thing that can affect rate would be the presence of a catalyst. You might have heard of a catalyst in biology class in terms of an enzyme. It's a protein that helps speed up a reaction. So these are something that speed up the reactions by changing the mechanism of the reaction, so finding a faster way to that to happen. But they're not really part of the reaction. They're not consumed during the course of that reaction. So to figure out a reaction rate, a simple way to do this is just to monitor concentrations of the reactants in your reaction vessel, or in your reaction wherever it's taking place, as a function of time. So you can see here we start off, we have all of molecule A at time 0. At 20 seconds it's about 50-50. At 40 seconds we've shifted to more of molecule B, and obviously that would probably keep going. And so what you would get is data something like this. So if we're looking in this reaction, we measure the concentration of butyl chloride, which is the reactant, at various times. So initially at 50, 100, and 150 seconds, and then this is how much we started with, this is how much is left. And then from there, we can calculate the average, the rate over the intervals, so how much has changed from 0 seconds to 50 seconds. So that's just your average rate, is just the change in the concentration over the change in time. So in this case, we've changed from 0.1 to 0.095 over 50 seconds. That's your delta t. So average for that time interval is 1.9 times 10 to the minus 4 big M over S. So a couple things to notice: that the average rate decreases as the reaction proceeds, which you should expect, right? Because as you're going along, you're getting much less of the reactant, so concentration is decreasing, you'd be less likely to find your partner, so less likely to react, so it would take longer. If we look at a plot of this versus time, we see that we get a curve like this, right? Which is what you'd expect, because it's getting slower as time moves on. It's not a straight linear relationship. And so the slope of a line tangent to this curve at any point is its instantaneous rate. And since reaction rates change over time, the best place to get the reaction rate is the beginning of the reaction. That's going to be the most accurate spot to get a predictable rate. So in this reaction, we see we have the molar relationship between the reactants and the products that we're measuring is a 1-to-1. So the rate of disappearance of C4H9Cl is the same as the rate of appearance of C4H9OH. So we're looking at our average rate equations here. We've got the change, the decrease, the negative delta of the reactants over time is the same as the increase, the positive delta of the concentration of products over time. By the way, something to note, when you see something in brackets like this, that signifies concentration of. So we're talking about the concentration of C4H9OH, and delta means change. So that's great if it's a one-to-one relationship, but what if it's not a one-to-one relationship? So an example of that is 2HI turning into an H2 molecule and an I2 molecule. So in this case, 2 moles of HI are going to disappear for every mole of H2 or I2 that's appearing. So HI is disappearing 2 times faster than the reactants are appearing. So in this case, it's disappearing at half the rate. So negative 1/2 delta HI over delta T is the same as the appearance of one of those guys, one of those reactants. So if you want to look at this in a generalized form, then for like reactant A, big A, the delta A over T, and 1 over little a, the stoichiometric coefficient. And since that's a reactant, it's a negative because it's disappearing. Same thing with the B, and then the products, the C's and D's, are appearing, so they're positives. So if you look at how the rate changes with changes in concentration, you can get some information that you can actually use to do something a little bit more useful. So if we look at this reaction here, NH4 plus NO2 minus yielding N2 plus 2H2O, and this is the data that we've generated. So we've done a bunch of different experiments, and we've got initial concentrations of NH4 plus and initial concentrations of NO2 minus, and then their observed initial rate. And you can see that they're not always different. Like the first 3 experiments, we changed the rate, or sorry, the concentration of NH4, left this constant. In the second 3, we changed the concentration of NO2 minus, but left these constant. So if we were to compare experiments 1 and 2, we see that NH4, the concentration of NH4 doubles, going from 0.01 molar to 0.02 molar, and the initial rate, what does that do? It doubles as well. Similarly, if we look at experiments 5 and 6, these are useful for figuring out something about the NO2 minus, because any change that's happening here clearly has nothing to do with this, because that didn't change at all. So if we look at these, we see that when the concentration of NO2 doubles, again, the initial rate doubles. So this means that the rate is proportional to the concentration of NH4 plus. It's also proportional to the concentration of NO2 minus. So overall, the rate is proportional to the two of those multiplied by each other. And so we can do something a little bit more useful with this and give it your reaction constant, your rate constant, which is K. And so this is our rate law. The rate is the rate constant times the concentration of the different reactants. K is the rate constant. And so we put this together, we call this a rate law. Okay, so if we have this generalized reaction here, the rate is going to be your rate constant times the concentration of one of your reactants raised to some exponent, and the concentration of your other reactant raised to some different exponent. This also shows the relationship between the reaction rate and the concentrations. So the exponents tell us the order of the reaction. So if we're looking again at this same one, the exponent is really just a 1. That's why we're not writing it there. So it's first order with respect to NH4, and it's first order with respect to NO2 minus. Overall, we would add up the exponents. So the overall reaction order is 2, because it's 1 plus 1. So it's a second order reaction overall. So a couple things to note about all of that there. One, you have to determine these things experimentally. You can't just look at the equation and figure out what it is, because the order of the reactant is not necessarily the same as the stoichiometric coefficient. If they are, it's a coincidence. If you look back here, right, I didn't say that K equals concentration of A raised to the A power. No, it's something different. So don't do that. And then something else with the orders, if it's a first order, that means that the rate and the concentration of reactants are directly proportional. So if you double one, you're going to double the concentration, you're going to double the rate. If it's a second order, it's not that relationship. It's an exponential relationship. So if you were to double the reactants, you would quadruple the rate. So how do you determine a rate law? Again, this is done experimentally, so you'd have some data to look at. So basically, you'd write out your rate law using variables for your exponents, and then using that experimental data, you can figure out what your variables are individually. And once you've done that, you can take any of the data from that experiment and substitute it in to figure out your K, your rate reaction constant, and then you're good to go. So an example of this is this reaction here. So we've got nitric oxide with hydrogen at 1280 degrees C. Again, temperature is going to be really important, right? Because if we were to change this temperature, we're going to change the rate, and we would have to have a new K. So this is only going to work for this particular temperature. So from the following data, determine the rate law, the rate constant, and the rate of reaction. So to begin with, we got to write out our rate law using our variables. Write out our rate law using variables. I'm going to pause and do that. Oops, that didn't work. Oh, crap. So to get our rate law, we'd start off by writing our rate law out with x and y for variables for the order. And so again, we know that we really care about the concentration of the reactants because that's what's dictating the speed. So we know our rate equals our constant times the concentration of NO to some exponent and the concentration of H2 to some exponent. So how do we figure that out? Well, we look at our data. So if we look at any of these experiments, we can try to figure out what's going on. So if we look at any of these experiments, we can try to figure out what's going on. So which one is more useful for which of the different experiments? So for example, if we're looking at the first two experiments, H2 remains constant. So this is going to give us some information about this guy down here, our x variable. So as we doubled our initial concentration, what happened to our initial rate? Well, 1.3 to 5, not quite a quadruple, it's a 3.8x, but we're going to call it a quadruple. So that tells us if we're going from, we're doubling this and we're quadrupling this, that means it's a second order reaction, so our x is going to be 2. And if we look at experiments 2 and 3, we're keeping our concentration of NO equal, so any change in initial rate has to do with our concentrations of hydrogen. We're doubling our concentration of hydrogen, and then we get a doubling of our initial rate. So it's a one-to-one linear relationship, so that's first order. So that tells us this is our rate law. We have NO squared and H2 to the first power. And overall, this is a 1, 2, third order reaction. So how do we figure out the rate constant? So now all we need to do is pick one of those experiments and basically plug those values into your rate law and solve for K. So here's our rate law, and I'm going to use the data from experiment 3. So we get setting equal to K. Here's our rate in experiment 3 is 10 times 10 to the minus 5th, big M per second. And these are our concentrations of our two reactants. This is the NO, and we're squaring it. And here's our H2. And solve K equals 10 times 10 to the minus 5 over 4 times 10 to the minus 7. It's very useful to write in your units because you're going to have to keep track of those units to figure out what your final units are for K, because they're going to be different depending on the reaction. And so overall, this is 250. And for our units, if we look up here, we've got 1m in the numerator up here, 3 m's in the denominator, so we're going to cancel out one of those and turn this into a 2, and then this is still in our denominator as well. So we can write it 1 over big M squared seconds, or you often see it this way, big M to the minus 2, S to the minus 1. It's equivalent, but same thing. So 250, and this is your units for your K. Now part C asks us to figure out how long a certain reaction, or how long this reaction would take given certain concentrations of reactants. So we have our K, so we can figure that out pretty easily. So we know that our rate is 250 big M to the minus 2 to the minus 1, and a concentration of NO squared plus concentration. Start over there. So now we're asked to figure out how long the reaction would take with a different set of concentrations. So now we have our K. That's relatively easy to do. Really just have to plug everything in. So here's our rate law with our K inserted in there that we just figured out. And so just plug in our values. So we got 250, and they told us to plug in this for the concentration of NO. We're squaring it. And this is our concentration of H2. And so our rate with sig figs is 2.2 times 10 to the minus 4th big M per second, which makes sense for rate, right? That's why I said it's change in concentration over time. But if you look, everything would cancel out. We've got 1, 2, 3 M's here, and then 1, 2 in the denominator, so we're going to drop one of them. So leaves us 1 M in the numerator, and then this is our S in our denominator. So a couple things just to think about. In general, a large K, so if a K is 10 to the 9th or higher, we call this a fast reaction, versus a smaller K, 10 or lower, we would call a slow reaction. If your K equals 0, well, that means your reaction is not happening at all. It has 0 rate. And things to remember is that the units for K depend on the particular rate law. So for example, just to practice with that a little bit, what are the units for this rate law? Here's just a random, kind of like one we were looking at, but a little bit different. It's a second order reaction. How do we figure that out? Well, just set it equal to K. K equals the rate over these concentrations. So rates is in big M per second. Concentrations are both big M's. So these guys, 2 in the bottom, 1 on top, cancel out. M to the minus 1, S to the minus 1. So you always want to watch your units so you can make sure that you're getting the right units for your K. So we're looking at changes in concentration over time. So if you're looking at a first order reaction, we know that the rate depends on the concentration of the reactants raised to the first power, right? So it's directly proportional. The rate to the concentration are directly proportional. So the reaction is A to the product. We talked about before the average rate is a change in concentration of reactant over time. Our rate law for this would be our constant times the concentration of A. The units for that would be 1 per second. And then so we can basically set those equal to each other. Rate equals this, which also equals this. And then if we use the magic of calculus, don't worry, you don't have to worry about doing any calculus here. We can use calculus to integrate the rate law. And so for our first order process, we now get this instead. So where A, concentration of A sub 0 is the initial concentration of A, and this is the concentration of A at whatever time t. And then this is the K is still the same. And then to manipulate this a little bit more, to make it a form that's probably a little bit more familiar to you, our good old y equals mx plus b equation of a line form, this is what it comes out to be. Natural log of A sub t equals negative kt plus the natural log of A sub 0. So if you have a first order reaction, a plot of the natural log of A versus time will yield a straight line, and the slope will be negative k. Why is this useful? Well, if you think about this example, this first order reaction where methyl isonitrile basically on its own is converted to acetonitrile. And so here's our reaction. If we collect the data for this over time at a certain temperature, this is the line we get, right? So it's clearly not a straight line. And we're not quite sure what order reaction this is. Well, if we were to graph the natural log of the pressure, pressure is just substitute for concentration, which is fine to do as long as you do all pressure or all concentration. When you do the natural log of the pressure plotted as a function of time, you get a straight line, right? And that's what we said happens with a first order reaction. So therefore, we can say that that process is first order. And if you want to figure out the k, you can just figure out the k is the negative of the slope, which happens to be 5.1 times 10 to the minus 5th per second. So just by graphing the data in different representations, you can figure out what's going on with the reaction. So for example, we've got the way so this is a way you can apply this. This might be something you might be asked to do in the AP. So a decomposition of a certain insecticide in water at 12 degrees Celsius follows first order kinetics. So we know we're dealing with the first order rate law with a rate constant of 1.5 per year. And so some amount of this insecticide goes into a lake on June 1st, leading to a concentration of 5.0 times 10 to the minus 7th grams per centimeter cubed. Assuming the average temperature of the lake is 12 degrees, which is convenient, right? We want us to figure out what is the concentration of this insecticide after a year, and then similarly, how long will it take for that insecticide to fall to a certain concentration? In this case, 3.0 times 10 to the minus 7. So how do we do this? Okay, again, we know this is a first order, so we can use our first order integrated law. So use that rate law to solve for the natural log of concentration A at time t equals 1 year. So the natural log of A sub 1 year, and you can plug in all your other values. So here's our negative, here's our rate constant, here's our time t, and here's our initial concentration, taking the natural log of that. And so you end up getting natural log of concentration of A at 1 year is negative 1.5 plus negative 14.51. So 15.96. And then to go from here, you use that little e button on your calculator. That's the inverse of the natural log. So e to the negative 15.96 equals your concentration after 1 year. 1.2 times 10 to the negative 7 grams per centimeter cubed. Also asks us to figure out how long it's going to degrade. Use the same rate law and solve for t, basically. But now we'll have a final concentration because we want to know what it's going to, and we know what its initial concentration was. So just plug in those values, and again, so here's the concentration at time whatever. We don't know what that time is. Here's your t, here's your one value, here's your initial concentration, here's your rate constant. And so this is what it looks like. And eventually we're going to get down to t equals 0.34 years. So you can do the same thing with a second order process. We're not going to go through the whole derivation, but if you were to integrate your second order rate law, this is what you get. And so this is in the same form, the y equals mx plus b form. The units for this would be 1 over a big MS, or m to the minus 1, s to the minus 1 is another way of writing that. And so if a process is second order, with respect to that reactant A, the plot of 1 over the concentration of A versus T is going to give us a straight line, and the slope of that line is going to be positive K. So if we're looking at this example, we've got some data here. So here's our reaction, here's the data that it gives us, and again, if we could just go the concentration versus T, or in this case we're doing a natural log, this is not a straight line. If this were a first order reaction, we would expect to get a straight line. It's not a straight line, so the process is not first order. However, if we graph 1 over the concentration, that's still wrong. Oh, shoot. However, if we graph 1 over the concentration of NO2 versus time, we get this plot. It is a straight line. So since this is a straight line, we can say this guy is second order with respect to that reactant. And finally, something you're going to see a lot less often, but you might see it, a zero order reaction. So this is something that is basically independent of the concentration of the reactants and is therefore pretty rare. So basically it's just A, so whatever your reactant is just degrading on its own, so it's turning into a product. So this is your average rate, right? And this is a zero order reaction. So basically it's just K. It's just based on, right? It's totally independent of the concentration of reactants. It's just a rate. So its integrated rate law is just going to be this here, and the units are going to be big M per S. Again, you'll see those a lot less often. Something else you can talk about a lot when we're talking about rate is half-life. You may have heard this in reference to like radioactive material having a half-life. It's the time required for half of the reactant to react, or if you're talking about a radioactive element, for half of it to decay. And because the concentration of A is 1/2 of that original concentration, we can write this expression here. Right? Your concentration at time t is 1/2 of your initial concentration. And so a first order process, we can do some calculus and come up with this equation here. And so again, for a first order process, the half-life does not depend on that initial concentration. It doesn't matter because this first order is proportional. So whatever you start with, it's all going to be the same. So you can do that equation right there. For a second order process, you would get this guy down here. Now it does matter. So the time for 1/2, your half-life, is 1/k times the initial concentration. Because for the second orders, it does matter. So an example of how you might use this. So if we're given this graph here, and we've got the reaction of C4H9Cl with water, and we're told it's a first order reaction, we want to use this graph to figure out what the half-life is, and then calculate that K, its constant. So how do we do that? Well, our initial concentration we get from the graph, right? At time 0, we've got 0.1 molar. And then we also have to get our half-life, which would be, well, we have to get our half-life concentration, which would be 0.5 molar. And so at that point on the graph is about 350 seconds, which is the number we really care about. So using our equation, time at 1/2 is 0.693 over K. We now know our time at 1/2, about 350 seconds. We can solve for K. And so our K is 2 times 10 to the minus 3 per second. So this is a nice little summary slide for you guys, just to put everything all in one spot. So the different types of reactions, different orders, their rate laws, their integrated rate laws. These are available on your formula sheet from the AP board, by the way. There's your units, and then to get a linear plot, this is what you would have to do. A zero order would just be concentration versus time. The natural log of concentration versus time gives you a linear plot for first order, and 1 over the concentration gives you a linear plot for a second order concentration. All right, so for part 2 of this one, we're going to talk about the mechanisms of reactions and how they work. So temperature, as we said earlier, as temperature increases, so does the reaction rate, because that K is temperature dependent. So anytime you have a K, again, it's based on a specific temperature. So if you calculate it for 100 degrees Celsius and you change your temperature to 50 degrees Celsius, you need a whole new K. So in a chemical reaction, bonds are broken, new bonds are formed, obviously, and molecules can only react if they collide with each other. And they have to collide with each other in just the right orientation and with enough energy. Right? Otherwise, you have to be able to make the bonds break, and you have to be in the right spot for new bonds to form. So example down here, these are your molecules before your collision. These guys collide, and they're going to form a Cl2, and this is your leftover stuff. But if this molecule, you can see, is rotated here, they come in and they collide like this, obviously you're not going to get a Cl2 molecule from this collision. Boing, just bounces off and no reaction happens. So that's why the more you're in motion, the more likely you are to A, run into something else, and then B, run into something else with the same orientation. And then if your temperature's higher, you're going to have more energy, and you're more likely to have enough energy to cause that bonds to break and new bonds to form. And so we call that the activation energy. So there's a minimum amount of energy that you need to make a reaction happen, right? So their analogy here is the golfer here. If he only gives a soft putt, the ball might not make it over. He has to give it at least enough energy to get the ball over the hump, and then he can get down to the pin. This is the energy basically that you need to stretch, bend, and then ultimately break the bonds so that you can form some new bonds. And we can use something called the reaction coordinate diagram to visualize this process. So if we're sort of thinking of these things in like a Lewis structure here, these are the bonds that we're working on. As you increase your energy, we can see what's going on with the products. So as we increase energy, we see that this molecule is starting to bend here. And at the high point, you've given it enough energy to break that bond. Right? This is called the transition state. This is where something called the activated complex forms, where these guys are ready to react with something new or react with themselves in a different way. And then now we're no longer putting in energy. Now, hopefully, we're getting energy out. And so the activated complex is free. It's crossed that activation barrier, and now it's basically it's a downhill shot for this to turn around, for this C to bond with this C now. And so down here end up with a net gain in energy. You're putting in energy going up and then coming out with energy. You get a net gain. Endo versus exothermic, we've used those terms before. If it's an exothermic, the products are going to be more stable than the reactants, so heat is going to be released. Heat exits the reaction. If it's endothermic, it's the opposite. So endothermic, heat gets absorbed, so our product has heat's being absorbed. It's not giving us energy back. These guys are going to be less stable in this case. And so an example of this, which of these energy profiles corresponds to the fastest reaction, basically. So we want to rank them according to their rates. We're going to rank these according to their rates. So right off the bat, I guess it's easiest to find which one is going to be the slowest or which one's going to be the fastest. Well, we know that this guy over here, well, so we know that we're looking for the biggest change in energy, right? So this guy is going to be our fastest reaction. Right? We get the biggest change. So, but when you go over here, we're looking at the same, 25 versus 25, delta change in energy, delta E, but this guy is going to be an exothermic reaction. So he's going to be going even faster. So the slowest one is going to be this guy. You have to put in the most energy, so he's going to be going really slow. These guys have the same amount of energy, but since this guy is an exothermic reaction, he's going to be the fastest. So 2 is going to be less than 3, is going to be less than 1. Okay. Moving on to reaction mechanisms. Reaction mechanisms is just what this says, is the sequence that actually happens to produce the reactant. So you might have some intermediate processes that aren't actually shown in your overall equation. So they might occur through several steps, or they might occur all at once. And so if it does occur over multiple steps, each one is known as an elementary reaction or an elementary process. And so we often talk about these in terms of molecularity. And so the molecularity of a process tells us how many molecules are involved. So something like this, one molecule is involved as unimolecular. And by the way, we're talking only the reactants, right? This guy would be bimolecular. You've got 2 of the same thing. This one has an A and a B, 2 different things, but still 2, so it's bimolecular. And then you can have different combinations of termolecular. So in this case, for elementary steps, now the rate laws are based on their molecularity because we know this is what's going on. Right before, we couldn't use molecularity, we couldn't use our stoichiometric ratios because we didn't know if there was a intermediate step or whatnot. But since we're using these as our intermediate steps, we can use those to figure out what's going on with the rate laws. So if it's unimolecular, it's a first order, right? And the rate is going to be this. If it's bimolecular, it's going to be a second order reaction, and the rate is either going to be Ka squared or Kab. If it's termomolecular, you really don't need to worry about it. They're very rare. It's beyond the scope of this class. It's very rare because if you think about it, you have to have 3 molecules colliding in the proper orientation with enough energy regularly for the reaction to happen. So you can see that's not going to happen all that often. When you're talking about multi-step reactions, one of the steps is invariably going to be slower than the others. And this is what's going to determine how fast that reaction is going to go overall. We're going to call it the rate determining step. So like in this diagram here, all the cars are bunching up at Toll Plaza A, but don't seem to be having too much trouble getting through Toll Plaza B. So we say that this is the rate limiting step, the rate limiting toll gate. Versus in this diagram, they're zipping right through Toll Pass A. They all have Easy Pass. They're flying through. But something's wrong with the Easy Pass lane over here, so they're bunching up. This is what's going to be dictating the speed of traffic. So in this case, this guy is the rate limiting step. So if we have a slow initial step, that makes things a little bit easier. So if we look at this reaction here, NO2 plus CO yields NO plus CO2. The rate law for this guy experimentally figured out is K NO2 squared. So does that really make sense with what you see here? No. If you were just to look at that, you wouldn't write this rate law. So that tells us that something is happening, right? CO is probably necessary for this reaction to occur, but the rate doesn't depend on it. Otherwise, it would be in our rate law. So it's not showing up there. So this suggests to us that this reaction is occurring in different steps. Something is happening that's not being expressed in the rate law. It's something's happening that's not governing the speed of this reaction. So a proposed mechanism might be for this. In step 1, you could have 2 different NO2 molecules combining to get NO3 and NO, this being our slow step. And then this guy, this NO3, would combine with the carbon monoxide to get your NO2 plus your CO2. In this case, we would say that NO3 is an intermediate, right, because it's only showing up in the middle, and it gets totally consumed. That's why it's not showing up in any of your products. And it's not involved in the slower step, so it's not going to appear in the rate law. And this slow step does jive exactly with what the experimental rate law was, which was K, the concentration of NO2 squared. So put this into an example. We've got this reaction here, ozone reacting with nitrogen dioxide. And so we think it's going to happen in 2 steps. These are our 2 steps. And so these are our questions. Why do we think, what makes us think this is a 2-step reaction? What's wrong with just writing out this way? Well, what did I say about molecularity? This is a termomolecular reaction, 1, 2, 3, and those are pretty rare. So you wouldn't expect that to be the case. And then the second part of this is the experimental rate law is K, concentration of O3, concentration of NO2. What does this tell us about the relative rates? Well, what does this match up with? This matches up with our first step, not our second step. So since it matches up with this, that's the one this is the rate law. That means the rate is based on this step. So this must be your slow step. The step 1 is your slow step. This is your fast step. But what if we have a fast initial step? Then it gets a little bit trickier. So if we're looking at this reaction here, 2NO plus Br2 equals 2NOBr. The rate law for this reaction experimentally is found to be K NO squared Br2. NO squared Br2, okay, that doesn't seem to make sense. Because it's a termomolecular process, right, it's probably not that. It suggests that it's a 2-step mechanism. So one proposed mechanism is this. Step 1 and step 2. We think the step 1 is a fast step, step 2 is a slow step. And notice that for step 1, we've got forward and reverse arrows here. That's going to become important. So the overall reaction depends on the rate of the slow step, like we said, which was step number 2. So the rate law for that step would be K sub 2, NOBr2, concentration NOBr2, NO. But how do we find this concentration? Right? We're not given that. That's just an intermediate that totally gets consumed. So is that helpful? Well, it turns out yes. So if we think about it, NOBr2 can react in 2 different ways. It can react with the NO to form the NOBr, which is what we saw in the rate steps, or it can also decompose and reform back to NO. And so the reactants and the products of the first step are basically in equilibrium with each other because that's the slow step. And so they're piling up there at that toll plaza. So as some get formed, some are also going to decompose and go back the other way. And so we can say that the forward rate equals the reverse rate in that slow step because it's being held up by that second step. So because of that, we can rewrite our rate expression like this. So K sub 1 NOBr2, which is what it was in the overall reaction, and then it equals the reverse of that. So if we solve for concentration of NOBr2, this is what we get. Right? So then we can take that expression and substitute into our NOBr2 in the rate law in our rate determining step and get this. All right? So this being what was our NOBr, put it all together, and we get K NO squared Br2, which was what our experimental rate law was. Finally, talk a little bit about catalysts. These are the last things we said that can change the rate of a reaction. So they can increase the rate of a reaction by basically they decrease the activation energy. They do something that makes it easier for the reactants to come together. They lower the energy somehow, so it's easier to get over that hump. They change the mechanism by which that process occurs. So one example is they sort of hold those reactants together and help break the bonds. So this is a catalytic converter, I think, is going on in here. So the carbon gets held on by this catalyst, and then you can add these hydrogens to the molecule, and we've changed that substance, right? So it's about making that reaction happen faster. And like I said earlier, we have probably heard of them more in the context of biology. Enzymes are catalysts in the body, and basically if this is your enzyme, it gives a spot for the substrate, whatever it wants to change, to lock in there, and then it can help those products be formed. It's like a lock and a key, so every enzyme in your body works with a specific substrate. And that is the end of kinetics.